to this computer. And then I'm going to try to share by AirPlay. My watch let me do it. Okay. Oh. Let's see if it'll let me do this one. Nope. All right. It was working this morning. So let's try to share my screen. By AirPlay. There. Yay. All right. So is everybody on? Can somebody online wave at me to make sure that it's there? And I'm going to go ahead and open the chat for questions. So if somebody wants to online, go ahead and give me a question. All right. Okay. I see some thumbs up there. All right. And so here we have our last slide we were on. Okay. So I'm recording this lecture. I'm talking to you live, and hopefully it'll be on YouTube eventually. So anyway, so thank you for coming live. Obviously, wearing masks is important. So if you can, please do. If you end up getting on Bobcat Trace and have to be out, that's fine. We have live streaming. Plus, we also have YouTube videos. So please follow whatever protocol is recommended by the university. I know it changes a lot. So just go ahead and figure out what the protocol is when you are there. I was exposed, so I had to stay home last week anyway. But both my daughter, my wife, and all three of us have tested negative for 3 days in a row, so they're all good. So that's why I'm here. But I'm gonna wear a mask anyway because I can lecture in a mask. Anyway, so that all said, we are, actually I need to turn that up so that it can hear me. So my microphone is on the computer here. So, all right. So I'm gonna try to, get as much of a lecture out to 3 different masters as possible, the online people, the video people, and the live people. So bear with me. Okay, so we're going to finish up chapter 1 first, and then this video will actually say chapter 2, part 1, because we're going to get into chapter 2 here pretty quick. So when we were talking about our hybridization, I said we had to look for shape, right? Because in our sp3 hybridization, we had S and 3 Ps. We have a total of 4 sigma bonds we can make. Okay. In our sp2, we had sp and then 2p, meaning we can make 3 sigma bonds with a leftover p. And that made something else, right? That made a pi bond. That p bond was a pi bond. Okay. And then we had sp2, where we only had an S and a P, which means it could only bond twice, but then it has to have 2 pi bonds. And we saw that that shape corresponded to the hybridization, and the hybridization corresponds to the shape. Okay, now that's the bonds themselves. So let's talk a little bit more about that with how we can predict the shape of the entire molecule using these same hybridization principles. But we have to take into account our Lewis dot structures, specifically where we're having lone pairs. Lone pairs are going to control our geometric shape, and they're going to help us show where our molecular or electronic zones are. So we want to pay attention to all of this. So we need to pay attention to our valence shell electrons, which are all the electrons we see in our Lewis dot structures. That's the first thing, right? And we need to make sure we also draw our lone pairs, because that's going to be important to our structure there. So that way we can start with looking at the geometry around our central atom. So most of the time, if we have small molecules, that central atom is going to be carbon, but we can identify any atom on our entire molecule and decide what shape it has, okay? So we need to pay attention to, number 1, how many sigma bonds we have, how many pi bonds we have, and how many lone pairs we have. We have to look at all 3 of these to figure out our whole system of geometry. Okay, so because electron pairs repel each other slightly more, because there's 2 electrons and they take up a little more room than other bonds, we're going to see that they're going to spread things out a little more than we would expect from their hybridization. So we're going to see a difference in the hybridization ideal angle and the actual found angle in our final molecule. based on how many lone pairs we have. Okay, so that being said, we have to take into account our number of bonds, our kind of bonds, our hybridization, and lone pairs. So that's going to tell us everything we need to know. Okay, so to start with, if we have two electronic zones, what kind of hybridization do we have? sp is 2 sigma bonds. It has 2 electronic zones. So that means our linear molecules are going to have sp hybridization. So right in there, sp, right? We have 2 opportunities for our sigma bonds, okay? So we have 2 electronic zones. Okay. In some molecules that don't follow octet rule, we might end up with less than 8 electrons, but it's still giving us that linear 180 degrees apart electronic zone. Now, we can also have this. This is a trigonal planar. Okay, we can have this 2 ways. We can have trigonal planar this way by doing an sp2 hybridization, giving us 3 sigma bonds, or we can have it in a molecule that only has 3 valence electrons. Either way, you're going to have what we call a trigonal planar structure, meaning that all 3 atoms that are attached to the central atom are all in the same plane, and they're all 120 degrees apart. That's as far as we can spread them apart, okay? So if we only have 2 things bonded to it, and we have a lone pair, that lone pair takes up space. It changes the molecular shape, but you still have 3 electronic zones, 2 bonds, and 1 lone pair. The electronic structure is trigonal planar, but now what is the molecular shape? It's actually bent because the 2 bonds make up the molecular shape. The zones make up the electronic configuration, okay? Now let's go to carbon. Carbon, we see that happens a lot, especially if it's sp3 hybridized, so it has 4 equal bonds. If it has 4 equal bonds, if it's sp3 hybridized, it has 4 equal orbitals. So it's going to have that 4 equal orbitals. So everything that's sp3 hybridized is going to have 4 electronic zones. Does that mean it's going to have 4 bonds? No. It depends on how many valence electrons we have. So we need to pay attention to what the hybridization is and how many electrons we have to play with. So we're going to play with that. And if we have all 4 of these bonded, we call that tetrahedral. So the electronic structure and the molecular structure are the same, okay? So that being said, if we have something like nitrogen, how many electrons does nitrogen bring to the valence shell? It's in group 5A, so it brings 5, right? So it has 5 electrons. It needs 3 more to make its octet. So it's going to bond 3 times, leaving those 2 electrons left over to make a lone pair. So it's sp3 hybridized, believe it or not, but the lone pair is up here. So that means the molecular structure is like a little 3-sided pyramid or trigonal pyramidal. Trigonal pyramidal. Trig for 3, pyramidal for pyramid, trigonal pyramidal. Notice the lone pair electronically is there, but doesn't count for molecular structure. Now, let's take water. Oxygen, 2 hydrogens on it. How many electrons does it bring? 6, because it's in group 6A. So it only needs 2 more electrons to make its octet. So it only needs to bond twice. But that means it has a total of 4 unbonded electrons. So it's going to have 2 lone pairs. So what does that look like? Well, gosh, that looks like this, where we have 2 bonds to fill its octet, but we have these 2 here. So the molecular shape is bent. But what's the electronic shape? Tetrahedral, because it's sp3 hybridized. Okay, shape, electronic shape tells you the hybridization. Number of bonds and number of lone pairs tells you molecular structure, molecular shape. Okay, so let's look at methane. Methane's the simplest carbon we have here. Carbon's in group 4. It brings 4 electrons. It wants 8. It needs to bond 4 times. It's sp3 hybridized. 4 equal orbitals. Brings 4 bonds, so it needs to bond 1, 2, 3, 4 times. So electronically, it's tetrahedral. Hybridized, it's tetrahedral. And it bonds 4 times. So the molecular structure is tetrahedral. The perfect tetrahedron is hydrogen. Methane right here, because it's 109.5 degrees from every little bond. Okay. If we did not hybridize, we would not have 4 equal 109-degree bonds. So we must be hybridizing. They must be equal, and they are spaced out as far apart as they can. Okay, so let's take our next example here, and let's do ammonia, just like we did before. It is sp3 hybridized. So how many electronic zones does it have? But we now have a lone pair. The lone pair takes up more space than the hydrogen does. So we're not in that ideal 109 degrees anymore. We are now a little bit lower. Imagine it, the blue lobe there being a little bit bigger, like a balloon kind of blowing up a little bit, pushing those hydrogens down slightly. So it's moving it out of 109.5 down to 107. Okay, and now if we ignore that lone pair, notice the structure we get out of it. We get this trigonal pyramidal shape, molecular shape, but it's still sp3 hybridized. Okay, so that's great, but it's 107 because it takes up so much more space. And then if we look at water, again, sp3 hybridized, 4 electronic zones. It needs to bond 2 more times to make its octet. So we end up with these 2 lobes taking up even more space. We went from 109.5 down to 107, down to 105, okay? Giving us that bent molecular geometry, okay? Yes?
Is the electronic structure still considered tetrahedral?
Is the electronic structure considered tetrahedral? Yes, because look where all those little lobes are. They look tetrahedral, and those lone pairs are in sp3 hybridized orbitals. So yes.
The bond angle is a little different.
The bond angle is a little different because the lone pair is slightly bigger. Okay, and one way to think about it is electron-electron repulsion, right? In that bond, that sigma bond, how many electrons do we have?
2.
2, okay, and they're shared between the 2 nuclei. And if they're shared equally, right, those electrons spend most of their time in between those 2 nuclei. So there's less of it being out here to kind of act as an electrostatic ball out on the side here. So these hydrogens here, those don't take up as much room because more of the electrons are in between the oxygen and the nitrogen. The oxygen and the hydrogen. But that lone pair, it's not in between anything. It kind of blows up a little bit. Got 2 electrons, it's going to fill that whole space, takes up just a little bit more room, pushes that out of that perfect 109.5 degrees. Does that make sense? Okay, so let's move on. So let's see. We need Lewis dot structure. We want to always draw those lone pairs in to look at hybridization. We're using our periodic table to figure out how many bonds we need. Carbon, nitrogen, oxygen, and fluorine all are sp3 hybridized when we play with them. Interesting, isn't it? So that means we can start predicting very regularly what the electronic configuration and what the molecular shape are. Questions on that? So again, it's not a mystery. It's following some simple rules. Now, where's boron on the periodic table? It's in group 3. Right? Does boron follow the octet rule? No. So it has 3 electronic zones. It brought 3 electrons in its outer shell. It does not follow the octet rule, and therefore it only bonds 3 times. So what's the electronic shape of boron before it bonds? 3 electrons.
Trigonal planar?
Trigonal planar. So it is not sp3 hybridized. It's trigonal planar, okay? So in that trigonal planar, we have 120 degrees between each of those. And it does not follow the octet rule. So it's only going to bond one time each to each one of those electrons. Its molecular structure is also trigonal planar. Its molecular structure is also 120 degrees. Okay. So boron in this case is not hybridized with sp3. If anything, it's sp2 and has an empty p orbital. Okay. So if we go to another one that breaks the rule here, we have beryllium. Beryllium actually is in 2a. It's way over there next to lithium. It's filling its 2s orbital by having 2 electrons in it. And it's going to share 1 electron with each of the hydrogens for a total of 4. It breaks the octet rule again. But because it only bonds twice, it only has 2 electronic zones, which makes it what shape? Linear. 2 electronic zones makes it linear. Okay. Now, we can have carbon in the same configuration, but we have to have a different hybridization. We have to have sp. So we'll have to pay attention to that. So let's look at this carbon dioxide. Okay. So it's 180 degrees. So right away, what do you think the hybridization is on carbon? sp, because it's got 2 bonds. Okay, now it has 2 bonds and they're 180 degrees apart. Well, technically there are 4 bonds there, right? Where do those other 2 bonds come from? Well, let's look at this. If carbon here in the middle is sp, that means there are 2 p orbitals that are not hybridized. We brought 4 electrons in as valence electrons. We want 8. And if we look at our Lewis dot structure, we have 8 electrons around carbon, so we have filled our octet. We have sp. We have 2 unhybridized orbitals, and we have 8 electrons around our carbon. So everything seems to be going okay right now, right? So let's talk about the first 2 bonds we build and here, these 2 electrons and these 2 electrons. Those are hybridized orbitals. So what kind of bond do we have with a hybridized orbital? A sigma bond. All hybridized orbitals are going to give us sigma bonds. And remember, the sigma bond is the bond that's directly between the 2 nuclei. So it's always the first one we make, and it's always the hybridized orbital. And each of those lines counts for 2 electrons. In our Lewis dot structure, every line between 2 atoms is 2 electrons. Never forget that. I'm going to ask that on a quiz. And some of you are going to get that wrong. So write that down. Okay, so we have 2 electrons on each side of that carbon there. And we said that carbon was sp hybridized. Okay, so let's call this axis that we've done this on our x-axis. So we have our sp hybridized orbitals along this x-axis here. Now, if there are 2 p orbitals, they have to not be in that x-axis, right? So I'm going to put one of these in the y-axis, up and down, and then one of these in the z-axis, which is kind of sticking out here and going back there. Okay, so just from the fact that we have an sp hybridized carbon means that we have 2 sigma bonds in our x-axis, and we have a p orbital in our y and a p orbital in our z. All right, so what do we do next? Let's look at the oxygen. Okay, just from the way this has, let's draw this lone pair out here and this lone pair out here. What molecular shape does that oxygen have around it? Trigonal planar, right? We have 2 lone pairs and a sigma bond, which makes it trigonal planar. So maybe what kind of hybridization would it have? sp2. If it has sp2, that means it has sp and 2, so it has 3 sigma bonds, or a place for a lone pair in a hybridized orbital, a lone pair in a hybridized orbital, and a sigma bond. But that leaves 1 p left over. So where's that p? Okay, well, on this side, let's put the p orbital in this z-axis. Z, 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 if you're from London. And we're going to do the other side. The other side is the same. We have 1, 2, 3 electronic zones. It's trigonal planar. It's sp2 hybridized. It has 1 p left over. Are we going to put that in the z-axis? No, we're going to put it in the y-axis. And I'll show you why. This is the y-axis. Okay, so our carbon is sp2 hybridized. It has to bond with those 2 p orbitals. What kind of orbitals do p orbitals make? Pi bonds are made by p orbitals. Unhybridized p orbitals make pi bonds. So what we're going to do is we're going to create a pi bond over here. Pi bond is always a p orbital that's unhybridized in this class. And this is going to pi bond here. So this is going to be a pi bond of the unhybridized p orbitals on the other side. Okay. This is a little different than acetylene. In acetylene, we had a carbon triple bonded to a carbon where both of the orbitals overlap between the same 2 atoms. In carbon dioxide, it proves you don't have to do that. The p orbital just has to be overlapped with another p orbital. And in this case, it's going to be 1 on 1 oxygen that's sp2 hybridized, 1 on the other oxygen that's sp2 hybridized. So our electronic structure is linear. Our molecular structure is linear. Our oxygen is sp2 hybridized. Our carbon is sp hybridized. It gives us 2 sigma bonds and 2 pi bonds. You follow every single word I just said. All right, that's important, knowing that those things. So electronic structure controls molecular structure and hybridization. They all go together. Do we see how they all go together? All right, so moving right along, we're going to go to chapter 2 now. All right, so that is the end of chapter 1. We're going to continue on with chapter 2 right here. Okay, now we're going to do something new. Get your phone out and go ahead and get this QR code. It's going to ask you one question. The question is, what's your seat number? And if you look right in front of you, there's a seat number on the different things. I think, are they all different? Are they all unique? Yes, they seem to be all unique. So in one of the other rooms, you have to figure out which row you're on and then which seat you're on and which plane of existence you're on, and your level of enlightenment, whether you turn blue or not. If anybody got that last joke. Anyway, so that's the only thing. This is Bobcat Trace for me. This is also attendance. And so it works best if you're already logged into one of the Bobcat Wi-Fi's with your net ID. It'll automatically spontaneously kick you up here. If you do not have a smartphone, that's fine. Just email me your seat number same day, and then I can follow you that way as well. That way it takes care of attendance, Bobcat Trace, and I really like looking at these QR codes on weekends because you can get little cats and stuff out of them. Okay, everybody has their phone down, so let's go ahead. If you're at home on the chat, don't worry, because all you have to do is be signed in, and I actually have a participants list for there. So that counts. So at home, you don't have to do this, and the QR codes will not be on the videos. Will not be on the YouTube, will not be on the Canvas slides. They will be in the YouTube videos. Okay, so we're going to talk about families of carbon compounds, functional groups, and intermolecular forces today, and we'll get to IR spectroscopy. Now, what we're going to talk about here is not really truly nomenclature. We're going to do that in chapter 4, but we're going to introduce you to the topic that everything has a name and there's a system to it, okay? And so that's what I want you to get used to. Everything has a name and there's always a system. It's not a black box. It's not a mystery. We just have to figure out what the system is, okay? So what we're going to talk about first is the simplest form that we've already talked about, which is hydrocarbons, things with carbon and hydrogen. Hydro from hydrogen, carbon from carbon, hydrocarbons. If it's got only hydrogens and carbons, it's a hydrocarbon. See, system, great. So now, in our case of hydrocarbons, which is our simplest compound, or our starting class here, we have one called alkanes. Alkanes means 4 sigma bonds to carbon. Okay, you have 4 sigma bonds to carbon. There are no pi bonds. All the carbons are sp3 hybridized. That's a 3. They're all sp3 hybridized. Okay, why is this the simplest thing? Well, 2 different elements, and they're all bonded the same way. So that's our simplest thing. And we call those alkanes, A-N-E, A-N-E. This red, this highlighted section here, A-N-E, tells us that we only have those sigma bonds, and we only have carbons and hydrogens. So alkane, hydrogen. Okay, so that's pretty simple, right? Now, we have to have a way of telling us that, oh, we have a carbon somewhere in our molecule that has a different hybridization. So if you have any sp2 hybridized carbons, preferably double bonded to another carbon, in fact, required to have double bond to another carbon, you're going to end up with a new compound. We call it an alkene. So that means you have at least one carbon-carbon double bond in your system somewhere. Does it mean only one? No, you can have multiples. You can have, if we go back to stick figures, you can go have double bonds here and here. If you have one carbon double bonded to another carbon, which means it's sp2 hybridized, you have an alkene, E-N-E. So A-N-E sigma bonds only. E-N-E, at least one carbon-carbon pi bond. And then if you have at least one carbon-carbon triple bond, it's a Y-N-E, a kyne, alkyne, Y-N-E, okay. So that means you have at least 2 carbons that are sp hybridized. Sometimes I say sp1 because only one of the p's is involved, just to make sure that you know there's 2 p's that are doing 2 pi orbitals. So you have 1 sigma and 2 pi's. Here we have 3 sigmas and 1 pi. Oh, sorry. 1 sigma and 1 pi between the carbons, 1 sigma and 2 pi's between the carbons. So we have alkanes, simplest, all the same hybridization. Alkenes, at least 1 carbon-carbon double bond. Sigma and pi bond together make a double bond. Alkyne is triple bond. 1 sigma bond, 2 pi bonds between the same 2 carbons. Okay? So those are our simplest forms of hydrocarbons. Now, are there much more complex combinations? Yes. And one of the ones that we're going to talk about, it's a special type of hydrocarbon, meaning it only has carbon and hydrogen on it, but it has different properties. And it has different properties because of resonance. Remember when we talked about resonance? Atoms don't move, but electrons do. So the one I want to talk about here, which we don't actually study a lot until next semester, is this one right here. When we have resonance, we can have those single and double bonds move around by only moving electrons. We're not breaking any sigma bonds. We're moving pi bonds and we're moving electrons, okay? Turns out these are going so fast around and around, you actually can't measure it going from a single bond to a double bond, single bond to a double bond. It's just all of a sudden, all equal. So if you think about it here, if we look at this, there'd be a pi bond here, and a pi bond across these 2, right? But then when they switch, they go to the other set. These come to here, these go to here, and these go to here. And if they're doing it so fast, we just say, well, they are actually in resonance all the time. And they save energy by being resonant. So there's stabilization in resonance. And so what it really looks like is this ring. We have those electrons just going around, constantly being shared between all 6 carbons in all 6 p orbitals. Okay, and so because of this resonance and this extra stability we get from it, we call the compounds aromatic. It actually comes from the early days in chemistry where these had actually different smells than other things. They were very aromatic compared to normal hydrocarbons, and that's why we got the name. Turns out we didn't figure out aromaticity and the resonance structure for at least another 100 years. Yes?
So despite the 1 pi bond, it's not considered an alkene.
It is not an alkene because it has resonance hybridization, resonance stabilization. Okay, it technically qualifies enough, but because of resonance, it doesn't react like an alkene. That's why it's different. Okay, so we're again going to discuss this in great detail next semester, but for now, I want to show you that this is another class of hydrocarbons. Okay, so we have, those are the basic hydrocarbons, things that only have carbon and hydrogen on. Any questions about that? Nothing in the chat. All right, so moving on. So now we have to start talking about putting things other than hydrogen and carbon in a compound. So we got to go back to electronegativity, okay? So electronegativity increases as we go over to fluorine and up to fluorine, right? Which means fluorine is more electronegative than oxygen, and oxygen's more electronegative than nitrogen, and then carbon's right there in the middle, okay? So when we talked about that carbon-hydrogen bond, we talked about whether it was polar, covalent, non-polar covalent, or ionic. And the qualification was the difference in those electronegativities, right? And so if we look at the difference in the electronegativity between the carbon and the hydrogen here, it's very small. It's less than 0.5. So we call that a non-polar covalent bond, meaning both the hydrogen and the carbon want the electron just as much. And so it's not a very polar bond, and they share those electrons almost equally. And a carbon-carbon bond's the same thing. So those are going to share the bonds almost equally. Okay, almost all the other ones have some kind of polarity to them, right? The break point is 0.5, right? So 0.5 to 2 is that polar, non-polar. So if it's below 0.5 in difference, it's what we call a non-polar bond. So that means if we look at nitrogen and carbon here, it's right at 0.5. So it's just barely a polar bond, but it's a polar covalent bond. And then carbon and fluorine is 1.5. So it's still below 2, so it's not ionic. So it's a polar covalent bond. Okay, so we understand polar covalent and polar non-polar covalent. Okay, so it's all about that difference. So how can we use that to our advantage? Well, that means that we can talk about bonds having equally shared electrons between them if they have these non-polar bonds. So your carbon-carbon bond, your carbon-hydrogen bond, your nitrogen-nitrogen bond, anything with similar or the same electronegativity, less than 0.5 difference, are going to give us non-polar bonds. Now, non-polar bonds tend to be less reactive because which side do you attack? I mean, where's the chemistry? So we're going to see that those maybe don't do as much chemistry as the polar covalent bonds. So you want to look for those polar covalent bonds. So when we're talking about polar covalent bonds, we're talking about a difference of that 0.5 or higher. Okay, so let's talk about something like carbon and nitrogen, okay? Or even carbon and fluorine as a greater example. That's the biggest difference we have between carbon and something. Because fluorine's the highest at 4, carbon's at 2.5, 1.5 difference. And what we see is that fluorine has a higher electronegativity, meaning fluorine wants electrons more, meaning that the fluorine is pulling electrons toward the fluorine, meaning that this is partially positive on this side. So we say that with a little delta positive and a little delta negative. The fluorine is pulling more of those shared electrons to its side so that it has more electron density. So it's partially negative on that side of the bond. The carbon is less electronegative and is partially positive on that side of the bond. So that means all polar bonds have a partially positive side and a partially negative side. And we indicate that with an arrow for that bond showing the partially positive side with the little plus on it. Okay. Now, if we look at nitrogen here, nitrogen is slightly more electronegative than carbon. Carbon is still the partially positive side, but the difference between this arrow and this arrow is pretty big. These are only 0.5 apart. These are 1.5 apart. So which of these carbons, the carbon with the nitrogen or the carbon with the fluorine, is going to have the greater partial positive charge? The one that's bonded to the fluorine, because the fluorine wants the electrons more. So we can see which atom actually has more of a positive, partially positive charge on it just by looking at this, okay? So the arrow indicates the direction the electrons are being pulled. The plus indicates the side that's partially positive, okay? So that gives us an idea about where that bond is, okay? So that means that bond is polar, and that's going to put more electron density on one side. So how does that affect the molecule itself as a whole? Well, if we take all these polar bonds and add them together, we can tell whether the molecule is nonpolar or the molecule is polar. But we have to have all of the polar bonds together. So what would that look like? Okay. So in a case with like methane, in a case of methane right here, let's start there. We have carbon with a hydrogen and a hydrogen and a hydrogen and a hydrogen. And the difference between those is 0.4. So what kind of bonds do we have? Non-polar covalent bonds, right? And so is there even a little bit of partial charge on that carbon? No, because it actually has a slightly higher electronegativity than there. But so there's not really any polarity. There's no bond polarity there. Okay, so that means that we have, that can happen. But what if we have carbon double bonded to oxygen here? I'm going to put the lone pairs here just for fun. Actually, always put the lone pairs when we're first starting out, so you know they're there. Okay, so which is more electronegative, oxygen or carbon? Just look at the periodic table if you're not sure. Oxygen's closer to fluorine, so we're going to pull electronegativity in that direction. Actually, let me change the color of that. We're going to pull electronegativity in this direction here, and so that's going to give us the partially positive charge. What about that other side? It's going to pull it to the oxygen again, right? So we have two polar bonds. Two polar bonds. Is this a polar molecule? Okay, so polarity, that arrow, technically counts as a vector. It has an X and a Y component. These two ones are going exactly opposite each other. They cancel each other out. So that means this has zero polarity because they cancel each other out. So you can have polar bonds and have zero polarity, or you can have non-polar bonds and have zero polarity. You have to look at where the vectors go. So let's look at a polar molecule with different vectors. Okay, let's start out with something like, let's do a carbon with a hydrogen here and a hydrogen here and a hydrogen here, and then a chlorine here. Okay, so do we have any polar bonds? Carbon and chlorine. So we're going to draw a polar area here. Do we have any other polar bonds in here? No. So that means all of these are zero, or effectively zero. And so our molecule has a pole in it, has a direction, has polarity. When a molecule has polarity, we call that a dipole moment. It's hidden in here, but it's dipole, D-I-P-O-L-E, dipole moment. What the dipole moment means is there's a permanent polarity to the molecule as a whole after adding up all of the polar bonds. Okay, so let's do it with something else. Let's do something like carbon with a hydrogen, with a fluorine, with a chlorine, and with a hydrogen. Okay, what shape is this molecule really? It's tetrahedral, but I'm drawing it flat just because it's easier to draw that way. And if we look at where our dipoles are, we have a big dipole there, a almost as big dipole here, zero here, and zero here. Okay. So each of the bonds is already accounted for, right? So this dipole has a component that goes this way. And so it has two components that we have. it'll go one in that direction and one in that direction. This has going one in that direction and one in that direction, which means these two partially cancel out. These two that are going more or less in the same direction add together. And that is the direction of the dipole of the molecule. We added the dipole components of each of the bonds together to get the dipole of the molecule, okay? And we measure that molecule in what we call divides, which is, it goes from 0 for nonpolar up to several, like 5 or 10 or 15, depending on what we're doing. Okay, so do we see that all we're doing here is canceling out a lot of our we're canceling out things that are opposing each other and adding things that are going in the same direction to get our polarity, okay? So what do we need to know about that? Well, if we look at it again, and we look at this electronegativity difference that we have, and we see in this molecule here that we only had one polar bond. It was between the carbon and the chlorine. Chlorine is more electronegative, so it's pulling the direction that way and giving a partially positive charge on our carbon. If we imagined the map of where the electrons were on the outside of there. So I'm another molecule, I'm coming in to get close to this other molecule. The outside of my molecule is 100% electrons. The outside of your molecule is 100% electrons. We're technically trying to repel each other, right? But on my molecule, I have part of my electron density is right here. There's more electron density in this zone because the chlorine is pulling more electron density toward it. So it's partially negative. Now, the other side of my molecule is right here. This is this side of the molecule, and this is partially positive. Okay, still electrons on the outside of there, but if I'm going to come close to this molecule, and I'm coming close to the partially negative side, which part of my molecule do I want to put toward my partially negative side of the next molecule? My partially positive side, right? Because instead of just being electron-electron repulsion, there's partially positive, partial negative. We get a little bit more interaction than if we just had those electrons. So if we have two nonpolar molecules that are completely like that, they're just seeing electrons and electrons. You have a polar molecule coming next to a polar molecule. They're going to try to align to get the partially negative and partially positive sides together. So polarity leads to intermolecular interaction, the interaction between two molecules. Okay. So if there's an interaction between molecules, that should change properties. A question back there? No? All right. So question in the chat? No. All right. So let's talk about that difference. Okay. So before, when we were talking, yes.
I have a question real quick. Why exactly does electronegativity go up to the right? I understand, like, if the atom is more heavier, why that would make sense. But why does it go to the right?
Okay. So why does electronegativity go up and over?
Just to, I know why it's because it's a smaller atom. It makes sense that it would hold it more because there's less things.
Right. So electronegativity is an empirically derived structure based on a lot of things. And so if we think about it, the fluorine, its outer shell is the 2s and the 2p, right? And it's sp3 hybridized, right? It's as close to the nucleus as it can be other than helium. When you go up to chlorine, you're now in the 3, the energy level 3, which completely encompasses. So it's further away from the nucleus. So fluorine holds those tighter because it is smaller, yes. And it has a full or near full shell, and it has the number of protons inside is closest to the 7 electrons on the outside. So as you're pulling it in and in, you're closer to that filled shell. Okay, so empirically, it's small and it is closest to having a filled shell. Okay, so that's just a general trend there, and size will play a role later on when we talk about acidity and bases. Okay, all right, that being said, excuse me. Okay, so let's talk about this structure again with polarity, and let's go back to that concept where we had those sp2 hybridized carbons that had double bonds in them. So in the case of those, we had a carbon-carbon double bond, and we said that the carbon-carbon double bond has restricted rotation around this bond because of that double bond. So what that means is we'd have to break that pi bond to get it to rotate. So instead of breaking that pi bond, we're going to say, well, this is fixed on this side and this is fixed on this side. If those were in, if the double bond wasn't there, those chlorines could rotate past each other. There's no reason. The sigma bond can rotate. Pi bond would have to break to do that. We can't do that. So what that's saying is we have this chlorine is on this side of the double bond and this chlorine in the double. So as we said before, if we draw an imaginary line through that double bond, if they're on the opposite side of that double bond, what kind of configuration do we have? Trans. They're on the opposite side, trans. So we call that the trans isomer. And if we drew the same thing here, but we put the chlorines on the same side, hydrogen, hydrogen, we would have the cis isomer. And again, draw that imaginary line and see that they're both on the same side of that imaginary line, and therefore they are the cis, and that's CIS. CIS. And sorry, gotta look at my handwriting. Okay, so we have those bonds. Those chlorines are fixed in space because we cannot break that pi bond without a lot of energy. And so let's look at its molecular polarity. So I'm going to draw the things. Let's see, we have a dipole in that direction and a dipole in that direction because the chlorine is more electronegative than carbon. But if we look at that, they are equal and opposite. They cancel each other out. We have zero dipole. Now, if we look at this one, we have this one here, and we have this one here. So that has a component going this direction and a component going that direction, component going this direction and component going that direction. These two going to the in the same axis as the double bond cancel out because they're going equal and opposite. But that means these two here add together. So we have a net dipole on our compound going centering the in between those two double bonds. Okay, so one has a dipole and one doesn't, right? That's going to affect its properties. This, if it's coming up to another molecule like that, it's going to say, okay, the whole molecule itself doesn't have a dipole. So how do I line up? I don't know. This one has a dipole, so it's going to say, oh, my chlorines are going to stack with the hydrogens on the next one, and my hydrogens are going to stack with the chlorines. They know how to stack up, and that changes their properties. Now, there's three things that change properties, like melting point and boiling point of compounds. The first thing is molecular weight, okay? As you get bigger, as you add more things, your molecular weight goes up, okay? The second thing that happens is you have intramolecular interactions, okay? So those intramolecular interactions are going to be more important. And the more different types of intermolecular reactions, the more it helps. Okay, and we have multiple kinds, and I'll talk about them as we go through them. So when we see our change in melting point or boiling point, there's a reason. It's molecular weight or intramolecular interaction. So let's look at our cis compound here. It has a, oops, let me change colors here. Cis one right here. It has a net dipole of 1.9 Debye. It has a permanent dipole. It is permanently like that. It always has a partially positive side and partially negative side. And what we see is the melting point. Now, the melting point is defined as the energy it takes to get molecules to slip past each other. Okay? So that just giving enough energy for these to slip past each other, go from vibrating together to slipping past each other, is melting point. Boiling point is breaking all intermolecular interactions. Breaking all intramolecular interactions. So in the case of our compound here, we have a melting point that's fairly low, -80, because they want to slip past each other so they can be in solution, so they can have a dipole-dipole interaction in between the molecules. And then we have to heat it up so much that they have to break all these intermolecular reactions. And so our boiling point is 60 degrees. There's a big difference between slipping past each other and breaking all bonds. Yes.
So it basically expands the temperature range that it can be in liquid form.
Not always, but in this case.
Okay.
Okay. The dramatic thing is molecular weight to interactions.
Okay.
Yes.
Does that mean that these molecules are generally less stable?
I don't want to answer that. We're going to talk about that in chapter 5.
Okay.
It's more complex than that.
Okay.
But in this case, we have a permanent dipole, and it actually makes it have more molecular interactions because that is a permanent dipole and it can interact with itself, other molecules better. So in this case, the cis molecule raises the boiling point because of its dipole. Nothing to do with stability. Okay. So if we look at the trans